Hello and welcome everyone to today's webinar about training large language models in Oracle Cloud Infrastructure. Thank you for joining us. My name is Tara Van Cleve and I am a Marketing Event Manager for the Developer Initiative here at Oracle. Today, we're excited to show you how to introduce your own custom data into large language models using OCI GPUs and open source technologies, and to explore the capabilities of Alpaca. We'll also be recording the session, and you'll receive the recording via the same email that you registered with. If you have any questions during the webinar, please drop them in the Zoom chat and Q&A areas, and we'll be ready to help answer them. Well, we've set up a channel as well in our developer public Slack called Oracle AI ML Services that you can access at the QR code or at bit.ly/odevrel_Slack. We'll leave the channel open after the event to contact us directly with any questions and to share resources with you. So to access the GitHub guide for today, I'll leave this bit.ly and QR code up for just a moment, but it's at bit.ly/guide-LLM for large language models. Okay. And today's webinar will be presented by Ignacio Martinez, data scientist advocate. So without further ado, I will hand it over to Nacho.
Thank you, Tara. Thank you for the presentation. So on the chat, on the Zoom chat, I will be looking at the Zoom chat and Tara will be looking at the Slack chat. So if you have any questions at any point during the session, just make sure to answer, because we're here. This is kind of a more informal kind of Q&A session, which is just going to be 1 hour long. So we just have 1 hour for this. So make sure to ask any questions that you may have. So if you have accessed Tara's link on the Slack, you should access this guide here, right? This GitHub repository. Just let me show you what goes on here. This is a repository that I created, kind of like a pet project, so I could do a lot of LLM stuff here. And I wanted to create a large language model that was able to behave like my friends. So my idea at first, and this started a couple months ago, like 5 months ago, when this technology was very popular, right? So, or it just got started. So my idea was just that I need a way to extract messages from my friends or my colleagues on Discord, and then use these messages in a way to alter the behavior of a large language model to kind of introduce kind of like an alter ego or a version of my friends in a large language models. Santiago asks, where will be shared the recording for later review? You will get an email with the recording after the session, if I'm correct. Tara will know more, but yeah, yeah, you will get an email. Okay, so just going back to the guide, this is a session that I wanted to show around large language models, how you can introduce this information, right? So I created this lab with the purpose of trying to simplify many of the things that are currently going on right now. At the time that I wrote this, which was in July, I found a big problem, right? There were a lot of repositories that you could find in GitHub, in open source and everything, because I'm always an advocate for trying to do the things for free. So instead of paying for ChatGPT, which would be the obvious option when you're trying to work with LLMs, I said, well, how about I learn my own way with open source so I can, do this for free, right? And also do some stuff at work that is fun. So a lot of repositories are very complex, or they have this kind of vocabulary that is kind of hard to understand if you have not done anything around large language models or natural language processing. So there's a lot of advanced vocabulary in those. And for example, this repository, which is LitGPT, it has 3.1K stars on GitHub. It's one way so you can use any of these models with their software. I found at the beginning that they had a lot of vocabulary that wasn't very concrete. So let me just read for a bit and then you will see what I mean. Fine-tune the model. We provide a simple training scripts, and then it says fine-tune /adapter.py, fine-tune /adapter v2, and then LoRa.py that instruction tunes a pre-trained model on the Alpaca dataset. Well, if you're new to artificial intelligence, these concepts might scare you a little bit. So let me try to explain what's going on here, right? In order to fine-tune, and let me first define what fine-tuning is. Fine-tuning is just a simple and cost-effective way to train a large language model, but instead of doing the whole training from the beginning, with fine-tuning, you will get the information from someone else's work or someone else's large language model, and then you will introduce your own changes on top of that. So that means that you are going to use someone else's large language model, or what I like to call a base model, right? So a starting point that you haven't worked on. Imagine that someone created, and it's just one example, but LLaMA is one of the large language models that are most popular right now. So someone else from Stanford, or from wherever, but yeah, in this case from Stanford, created the large language model and trained it for, let's say, 100 hours, right? And then I come without any knowledge or anything. And the good thing about training and fine-tuning is that there is a technique called transfer learning. And with transfer learning, the good thing is that you can take over someone else's work without a lot of effort. So imagine that they have trained it for 100 hours. Then their neural network, which is, of course, this behind the scenes, this is, of course, a neural network on the background. It will have some numbers, right, which will represent the state of the neural network at the beginning. And then after 100 hours, these numbers will have changed, which is just basically a matrix. Matrix representing values, and the neural network will know what to do with these values. But the important thing is that I'm taking a neural network that someone else trained, and then I can use it with my problem and incorporate the data that I want. So in this case, we are going to create some kind of medical GPT, what I like to call it, like good doctor GPT or things like those, which is going to introduce my data. And we're going to talk about data right now. We're going to use as data this data set, which is open source, right? It's a medical question answering data set with 47,000 QA pairs created from 12 NIH websites. Let me explain a little bit more. Basically, someone else, this woman here, she created, and let me see one sec. I have a, yeah, let's, oh yeah, someone raised their hand. Don't see your question, but you can ask the question on chat if you want. So MedQuad is a data set with 47,000 question answer pairs, right? So they are taken from this 12 NIH website. So for example, if I go into cancer.gov, right, I see here that there are a lot of cancer types, etc. So imagine that I'm looking for, I don't know, bladder cancer. So someone has taken this website, this whole website. It has gone section by section, in this case, bladder cancer. And then it has scraped or parsed all this information, this text information, with an HTML parser. And then it has put them all into XML files. So let's go into the cancer.gov. So this would be a directory only for cancer-related questions and answers. Let's say, for example, this is an XML file which represents one question and one answer pair. In this case, they parsed the following question: what is or are chronic myelogenous leukemia? And then the answer here, right? Which is what we want. But I don't really like XML, right? It's not a very friendly format in order to manipulate your data. So the first thing I did is to build a parser. So I built this parser right here, which basically went one directory by one directory after downloading the medquad directory. And for each one of the sections, it just obtained, and I mean, it just went through the whole XML, obtained the question here and obtained the answer here, and then just put it into a dictionary in JSON format, which is more my style, you know? So in this case, let's see, for example, that I got an instruction, and this instruction is going to be constant for my whole problem. I want to keep the instruction as just a directive for the large language model to understand what it has to do on each one of the questions and answers that I give. And the reason I want this to be constant is that if it understands that the domain of my question is going to be around medical expertise, then I'm assuming that it's going to also acquire some of the, you know, vocabulary or anything also present in the base model. So just as a recap, I'm taking a lot of XML files, which you can see here, right? We have hundreds and hundreds of XML files, and I'm putting each one of these questions plus answers into a JSON file. So this would be the result of the running the parser across the whole medquad repository. So in this case, you see that the instruction is going to stay constant, right? Then the input is going to be the question in the XML, and the output is going to be the answer. And as you can see here, each answer is going, of course, is going to have a different length. There are some answers that have or appear to have a lot of tokens, and this is something that we will need to consider because we can also specify, we're also going to be able to specify the maximum length of the generations on our large language model after we do all the fine-tuning. But yeah, once we have these JSON files, we're going to go back to the guide. And so now you know what kind of data we're using, right? Questions and answers. We just want to give the large language model one question, and then it should return the closest thing possible, or as close as we want, to the original answer in our data set. And I mean, it doesn't have to be medical data. Remember that it can be any kind of data. You just have to have it in a format that is convenient for the model that you're going to try to use. So in our case, we are going to use Alpaca LoRA. I mean, an Alpaca is a format, a chatbot format, or a question answering format. So if you have any other problem that you want to incorporate data with, but it is not conversational, it's not designed for conversation, then you need to find another format which is not Alpaca. In this case, you will need to find, you know, there are hundreds and hundreds of formats. I will show you the most popular ones so you can decide which one fits to your problem the best, right? So the thing here is that we will use the Stanford Alpaca dataset, the data format. So in this case, you see that we have this adapter, and LoRA here. So why are adapters and LoRA inside the fine-tune? How are they related to fine-tuning? Well, as we said, fine-tuning is a very inexpensive way to do training with many less hours of training as well, because you are resuming the training from someone else's work or someone else's checkpoint, right? And with the checkpoint, you are just getting their neural network weights, and then you are just updating them in one way or the other. And the adapter and the LoRA are just two different ways to update these values from someone else's work. Then it says that we would need to download the data and generate an instruction tuning dataset. Well, in this case, we have already downloaded the data, right? We had it in XML format, then we transformed it into JSON format. And then we generate an instruction tuning dataset, which is basically just preparing your data for the Alpaca format. So if you didn't know that Alpaca had this format, well, now you know that it requires 3 things: the instruction, the input, and the output. In case you are working with other format, then just make sure that you know which instruction tuning dataset and what the format is, so you can prepare your whole dataset for that, right? So then it says that it is expected that you have downloaded the pre-trained weights as described above. And with the pre-trained weights, it just means the values that represent the neural network. This is what we mean with transfer learning, right? You are getting the pre-trained weights with someone else, from someone else, and then you are updating them. So just as a recap, right? Let me open this screenshot here, and just as a recap, right? Instruction tuning here is a type of fine-tuning that focuses on instructions and responses, because we are working with the Alpaca dataset, right? The pre-trained weights here, they are just values from a trained NN that let us use the pre-trained NN without any knowledge of how it was trained previously, right? Then the instruction tuning dataset is what we were mentioning, right? Instruction plus response pairs. And they are going to be introduced with a tool, an open source tool that we're going to see now. And LoRA and adapters are just 2 ways to perform fine-tuning. And we'll see that LoRA is really, really, really clever implementation. So yeah, I also wanted to mention that there's also probably the need for you to run a lot of Python scripts with a lot of variables and a lot of parameters. And it's in each one of these GitHub repositories that you will find in open source, then you have to, kind of get used to some of these concepts, because they're going to be similar in many of the repositories. So let's see, what kind of things these are. So the repositories that we are going to use today are, well, the most notable repo that we're using today is the Ubabugas web UI. I know it's a funny name, but yeah, this is a pretty famous guy right now in the LLM space. This repo, as you can see, is very popular. It has almost 25,000 stars, and it's a Gradio interface. If you were at the precursor or the beginning of Stable Diffusion, which was for generating images, like Midjourney and all of these image generation AI systems that existed. Well, Stable Diffusion Web UI had a very similar interface and was created like this, right? But Stable Diffusion allowed you to create, with some prompts, it allowed you to generate pictures, right? So Ubabuga is doing the same, but with text generation. So I want to use this Gradio interface for this. Tanya says, what will happen if you use text without any input or output attached? Do you mean on Stable Diffusion, or do you mean on the text generation web UI? So if you mean Stable Diffusion, you will probably not get any result. But if you were to use text without any input or output here, right? So just give it the instruction. Probably what will happen is that, since a large language model's focus is just to predict the next most probable token for you, right? In case that happens, probably the generations every time they will be different. So it will just print random stuff that it finds conventional, but to you, it will not look random, because since all or most of these models have been trained on huge amounts of data, they have enough literature and enough context and enough words and vocabulary to not bore you. So it wouldn't look random to you. So anything that the LLM says is just randomness, right? It's just predicting whose token is the most probable, or the one that fits the best after another token. So if you just put the instruction but no input output, I mean, the output is the thing that the LLM generates in the end, right? But for fine-tuning, you're not really interested in anything that has the input or the output empty, because this is the actual data that you're doing the fine-tuning on top of the base model, right? So if you want to enrich your base model, you need very good quality of your data here. The more data you have and the more quality each one of the input-output pairs are, the better for you, right? So I would just say that it would be a random question, but you wouldn't see that it's random. You will probably look like a very normal response from someone, but it will be on random topics each time. I hope that answers your question, Tanya. So going back to Ubabuga, right? And just to let me show you what's going on here, right? This is, I have an OCI GPU. I have two GPUs actually. I'm using a cluster of two NVIDIA 8100 GPUs, which is a bare metal instance, bare metal 2.2 instance on OCI, if you're interested. And what we are doing on this problem is just using OCI infrastructure, right? OCI GPUs as the underlying infrastructure, as the compute power of the problem, right? So this is my machine, my OCI machine, where I upload all my data, I download my repositories and anything, and I'm connected through SSH into here. So this is my machine, right? Things to consider is that I created a Conda environment called TextGen, and with this TextGen, I install all my dependencies and everything there. But the text generation is just the text generation from Ubabuga, an older version, because now I'm experimenting something else with a newer version, but it doesn't matter. The important thing is that whenever you download the repository and you have all the code here, right, you can create a new Python environment with Conda, you can activate the environment, then you initialize the new environment as bash. Then you check that you have all the NVIDIA requirements to run GPU things on it, GPU software. I really recommend, if you don't have, or if you're planning to do a clean installation on OCI, I really recommend this data science all-in-one GPU image. You can find it on OCI. GPU, it's a data science all-in-one, which already comes with NVIDIA, it comes with Python, it comes with Conda, with Jupyter notebooks installed already. So if you install that image, instead of just installing, canonical Ubuntu or any other operating system, it's much more convenient for you because you can just skip all the NVIDIA SMI, all the NVIDIA dependencies, all the libraries. You can just skip the whole thing and it will be already installed for you. So it's really good. Then I activate the TextGen Conda environment. I clone the Ubabuga's repository. I go into there and I install the requirements, making sure that whenever I'm installing the requirements, I'm in the Conda environment that I actually want. Then just some CUDA toolkit dependencies in case you're, outdated or you just don't have CUDA installed. You have to make sure to install it. And then we'll briefly talk about GPT quantization, which is a way to reduce the size of the whole training or the fine-tuning process. We'll go over that. But if you want to use quantization, if you have a low-end computer or you don't have a lot of resources, then I also recommend for you to install this secondary repository, which is completely optional, but it's very good for you. And also here you have a guide on the repository, right? It's called run on low vRAN. Where is it? Hold on. Yeah, here. So if you don't have, you probably may want to experiment on an OCI free tier account like Redorner, and you only have access to CPUs for the moment. Of course, I dearly recommend that you use a GPU for this, because we are using large language models, and this is a new dimension on artificial intelligence. I would say that it's one of the most hardest, most computational intense workloads that you have on artificial intelligence. So, I mean, but just in case that you don't have a GPU available and you have to work with CPUs, you can also try this guide in order to run the repository if you don't have a lot of VRAM, I mean, not a lot of RAM, or if you only want to use CPUs, you can also try to install DeepSpeed from Microsoft here. It's a way to reduce the memory usage of GPUs on large language models. And it looks like if you are running DeepSpeed, it will look like you are using a 6 gigabyte RAM on your GPU. So there are some ways to work around the GPU wall, but I really, really recommend that even if you have at home a computer or you have your laptop and you actually want to use this in a decent speed, then I really recommend that you try it out. Then after setting up CUDA in case you have any problems, and then here I have this download model.py, which is from Ubabuga. Right here you will have this download model file, and with this you can just download any model that you want from Hugging Face, which is awesome, right? Many of the Hugging Face models, they have this, which is the user and then the model name. So I can just download any of the models in Hugging Face with this tool. And of course, I need to choose a model that is going to be good enough to answer the questions without any basic stuff failing. So imagine that I'm asking the model a question in French, but it doesn't know French. Then of course it's not the right model for me, right? I need to make a decision which is going to be the base model that I'm going to do the fine-tuning upon. And then just after that, then I just run my server. I just tell it, please allocate as many GPUs as you can see. This is good if you have more than one GPU. In my case, I'm using a cluster, so it's very good. Also, I wanted to add the model menu so that it's easier for me to manipulate the interface in Gradio. And then I wanted to load on 8-bit, which has to do with quantization. But basically, and before we go into that, but as you can see, if I go into my Tmax instance here, this is already running my Gradio interface. And let me just show you that you have to do something in case you have just downloaded the repository, right? You want to run your server.py. Here I'm just going through the code, right? This is the actual code of the application. But there's one thing that you need to change. So if you go into the launch function, you see here, I don't know the line number, but you say that by default, the share value will just be a parameter here, which was like share.args.share, which is just a Boolean variable that tells the Gradio interface whether to share it publicly, like to the internet, or just share it locally. So if you're running this on your laptop, then it doesn't matter. You can just access with the localhost IP. But if you're using this on an OCI instance, then of course you need to change the share value here to true so that you can access it through a browser instead of just accessing in a weird way. So just remember to put share equals true here if you want that. But yeah, once I go into my interface, I can just copy this and I will have access to my you see that I was doing some test generations before, but you see that it's already running, and this is my text generation interface here. You see here that I have a session. I can even install someone else's plugins so that it's better for me. For example, a gallery to upload different things, Google Translate with an API key, Whisper STT, speech to text. There are a lot of things that you can install. Then this is the training training tab, which we are going to use to actually run the fine tuning, and I will show you which ones are the best parameters to run here. Then the model selector, if you have more than one model and want to switch, and then the LoRa's. Let's first of all, let's go about what a LoRa is, right? So LoRa is the technique that we are using for fine tuning. Do any of you have still have any questions about what the difference between fine tuning and training is? If you have it, now is your time to ask because this is going to get interesting. Let me just have a drink of water. Okay. So LoRa, right? Low rank adaptation. It's a way, and I mean, of course, there's a whole paper, and sometimes I feel like an imposter because I don't know these things as well as the actual people that designed this. But low rank adaptation is just a way to fine tune a model in a very efficient way. And, you know, you see that these models on Hugging Face or anything, you see here that I have a 7 billion parameter. You see that here is a 7B, 13B, and 7B here. This actually means the number of parameters in the neural network itself. So 7 billion right now is considered very low. There are some models with 50, 150 billion models, billion parameters. Like I think that I was discussing with someone that GPT 3.5 had 150 billion parameters. So you see that 7 billion is not a lot, but still is a lot, right? 7 billion parameters in a neural network is still a crazy amount. But just to give you an idea of what low rank adaptation does is that you see here that GPT-3 has 175 billion parameters. So with low rank adaptation, we are going to take about 0.1 to 1% of these parameters. So in this case, we would be talking about like 1.75 billion to, let's say that we take 1%, right? We take almost 2 billion parameters, and these 2 billion parameters, we are going to inject into each layer of the neural network. We are injecting a rank decomposition matrix. So the rank of a matrix, just as an FYI, the rank of a matrix is the maximum dimension of the matrix. But if you have columns or rows, they have to be linearly independent between each other, right? So let me just show you here this great article, right? Here is a good example, right? You have a matrix that is 5 times 5, right? This matrix is times 5 by 5, but the rank is 2. Why is the rank 2? Because, for example, you see that this row and this row, they are linearly dependent, right? This row is just half of the fourth row. So these two lines would not be independent. So the rank of the matrix is actually not 5, it's less than 5. So a rank decomposition matrix, what is actually going to do is just try to find or reduce the dimension of the decision-making process of each one of the layers so that it arrives at the actual token that you want faster. So basically, it's just a way to optimize the whole thing, right? So I'm taking 1.75 billion parameters here, I'm freezing the weights, and then I'm injecting this rank decomposition matrix. And that's in turn going to reduce the number of parameters that I need to retrain in order to incorporate my data. Right? So it's a little confusing. You just have to understand that it's one of the best techniques that are right now in order to perform fine-tuning and to introduce data into a base model. And there are a lot of, there are some others, but this is the one that LoRa, it works very well with LLaMA. And LLaMA is one of my favorite models because it was one of the first models that actually went open source since January, which was, the big boom on large language models. So LoRa is what we are going to use, right? So just to give you an idea of what's going on here, on the training part, of course, I need to make sure that whenever I'm doing generations, my model has to be selected. I got this model from someone else. It was a YouTuber called Amon Aegis that suggested this Neko Institute of Science LLaMA 7 billion Hugging Face model, which is a different or a variation of the Decapoda Research LLaMA 7 billion Hugging Face model. And it works a little better with medical because the people that did some fine-tuning to this base model, they were applying it to medical purposes and stuff. So I really recommend that you download this repo. It's purposefully very bad. And what I mean with very bad is that it's only 7 billion parameters. So it's not very huge. It's not a huge model. And this is actually on purpose so that I can show you that after you apply the LoRa, it doesn't matter as much how good the base model is. It's more important how well your fine-tuning has gone and, you know, the kind of these hyperparameters that I will show you. But just make sure that once you load the model, you allocate here your CPU and your GPU memories. In my case, I have 8 gigabytes of RAM allocated for each one of my GPUs, and then 93 gigabytes of RAM for my CPU, just in case I also want to offload some of the work to CPUs, right? Of course, you can also try to load in 4-bit, and this has to do with quantization. I will just, the last 5 minutes of the session, I will show you what quantization is. It's really interesting. It has been done a lot of times. Of course, you just take some bits out of the equation, and then you represent the value or the number, the same number, you represent it in less bits, losing some precision in the process, but you can argue that the precision that you lose, you gain with performance and everything. So for training, right, I have here an formatted dataset or a raw text file, right? So even you could, if you wanted, you could just give it a raw text file, like a .txt file with a lot of data that you had. And then that is also going to incorporate that corpus or that data into the model itself. But if not, if you have just followed the process like me and you're working with JSON format for Alpaca, then I really recommend that you use this formatted dataset tab here. And here I can show you that what I'm getting, these outputs, are the same that I have here, right? This after doing the parsing from XML and putting them all into one JSON, then I can just select it here. Imagine that I want to make a LoRa only for cancer patients, right? Might be interesting, right? Imagine that you have a client that works in a cancer research facility, then they are just interested in fine-tuning their model with some cancer questions and answers, right? So it makes sense to maybe only use or create a LoRa for a specific domain, right? So I really recommend that the rank of the matrix, and this is the maximum amount of rows or columns in the rank of the LoRa matrix. I really recommend this to be 64 or 128, probably like 128 here. So the rank of the matrix is going to be, I mean, the higher, of course, is always going to require more computational power and, of course, more RAM in order to store all the values in the matrix. This should always be probably twice the rank. So in our case, it should be 256. And the alpha is just the alpha of the LoRa is just a value that indicates that the rank of the matrix is a ratio between the rank and the amount or the scaling factor of the LoRa. So if the LoRa is higher, of course, it will mean that it's going to try to scale at least twice the size. And of course, you don't want to have the rank and the alpha the same. So I really recommend that you have 128 or 64 here, then double, and then probably double or not. This depends only on you, right? If you have a cutoff length of 64, it means that every generation that you do with your large language model in the end will just stop generating at 64 tokens. And one token is one character, right? So if your answers, I have some answers here that are pretty long, right? So I probably want to keep this at 256. And I also want to give it a number of epochs. This is just like in any transfer learning in artificial intelligence, how many times I'm going to give my neural network the data in order for it to see and try to understand and learn from it. So the more times you give it the data, the better it will be adapted to that. But I really recommend not really overdoing it, right? So imagine if you give like 5 epochs, I think that that's more than enough for this problem. And important, the learning rate, if 10 to the power of -2 is very high, is too high, actually it would introduce some overfitting into your model. And 10 to the power of -6 is very low. So a value in between, like 5 to the power of -4, 5 times 10 to the power of -4, or 3 is very standard and very good. So for content, sorry, for content upgrades, just remember that the most important value is the rank of your low rank adaptation matrix. So after, if I just run this here, and you can of course just also change the optimizer if you are looking for different optimizers and everything, but it's not really necessary. So if I did this training here, if I run this, it would take about 3 to 5 hours, depending on the number of epochs here. So usually it's like 1 hour every epoch that you give it with this value on the LoRa rank. If you increase the dimensions or the rank of the matrix, of course, it's going to be higher and higher exponentially, because the dimensions will just double column-wise and row-wise, right? So just to give you an idea of what's going on here, the parameters, in order, after doing this, and of course, I'm not going to run this because we wouldn't have enough time, but I already have some LoRa's created here, right? My TGD LoRa V3 cancer, which is of course specializing only on cancer research. And this is the LoRa that I created after running fine-tuning with LoRa. So just to give you an idea of the generations that the base model gives without any fine-tuning, I'm just going to show you an important parameter. And of course, all of these are important, right? But if you want to actually make some generations and be able to compare the changes between them, you need to keep the value in the seed constant, right? If I put -1 here, every seed is going to be different upon each generation. So that means that my generations are not going to be consistent. So I cannot deduce anything from my models. I need some consistency there, right? So my seed is always going to be constant. You can just specify any number here that you want. But remember that when you are doing on this text generation here, if you are doing some generations, the seed needs to stay constant. And also, the temperature is very important. The temperature, the top P and the top K are the most important or deciding factors that you can use in order to increase or reduce randomness on the model. So the higher the temperature is, the more creative the model will be. And the lower it is, the more it will stick to the original answers if it finds a reference on the fine-tuned data. And you have here a glossary if you want, and if you are using it, but just like I said, it controls the randomness of outputs, the temperature. 0, it's completely deterministic, and if it's 1, it will just try to do a lot of backflips and everything with the vocabulary. The top P and top K, which are very closely related, are very similar, right? The things that the higher value, the higher range of possible random results, because you are including more tokens in the probability domain. So what I mean is, imagine that I put top P equals 0.1, then I'm just going to use the 10% most used tokens in my training data. And the top K is similar. Sorry, the top K is just what I said. And top P is just those tokens whose probabilities are higher than P. So if it's 1, of course, it's going to be more random in both cases. And if it's very low, it's going to be smaller, right? So in my case, I want the generations to be as close as possible to my original data so I can try to see how much difference my fine-tuning process is doing, right? So with all these things considered, I could just make a generation, right? And this is the format for asking Alpaca things, right? And you see here that there are hundreds and hundreds and hundreds of different formats. Alpaca with input, Q&A, instruct Alpaca, which is a variant for instructions only, Blue Moon, ChatGLM, Galactica, Guanaco, which is another variation of Alpaca. You also have LLaMA v2 here already, Open Assistant, Orca, which is another very good open source model, etc. So depending on which one of these models you're using, remember that the structure of the questions that you have to give the LLM, they also have to change a little bit, right? So if I do these generations here, and this is actually the format that I want, and I click on generate, then this is going to start generating. So Christopher says, would any parameters have to be changed if you were dealing with sensitive data based on HIPAA laws? There are some ways in which you can specify if you want some tokens or some strings not to be generated. You can also, I don't remember here, but I read this in one of these no repeat engram size or something like that. There is a way in which you can remove some data, like remove some specific keywords. But if you're dealing with sensitive data, there is like no one thing that would just magically make the sensitive data disappear, right? So I would say that it's kind of 50-50, right? You have to be very careful of the data. But if you are doing fine-tuning, your fine-tuned data set is going to be smaller than the actual, big one. So it's easier for you to control a little bit, right? I hope that answers your question, Christopher. So just to give you an example of what the answer was the chronic lymphocytic leukemia is a cancer of the white blood cells called lymphocytes, blah, blah, blah. Okay. But you see that I asked it how you can diagnose it, and then it just started rambling about like a definition and stuff. So the base model was actually able to answer without any LoRA applied. So it's able to answer questions in English. It's able to answer somehow. I don't know if this is 100%. I'm not a doctor or anything. I don't know if this is actually correct. But I know that the main point of the question, which was how do you diagnose it, it's not present here in my answer, right? So now what I'm going to do, and of course, I mean, just to show you that the seed state stays constant, if I start generating this again, the response should be the same, right? The chronic lymphocytic leukemia, CLL, etc. Then it will just start generating the same again. So now that I'm keeping my seed constant, I'm stopping the generation and I'm applying the LoRA to my model, right? It shouldn't take long, right? It's already, let me see here. It's applying. Yeah, it's already applied. So now if I generate it, and sometimes this bugs, but if I generate again with the LoRA applied, then the response should change. So you see here that the response is actually changing, which means that the LoRA is actually kind of useful. And we are not sure 100% if the data that we are giving it is great. Of course, it's taken from the internet, from these .gov websites. So of course, the data is always going to be biased from whoever wrote it. But you see that at least the LoRa is changing the values of the neural network because it's taking a different path in order to arrive to the answer, right? And you see here that it's actually answering me, okay, how I can start the diagnosis for chronic lymphocytic leukemia, which is awesome, right? Because just with 2 or 3 hours of training and fine-tuning, I'm able to incorporate or create a LoRa that actually increases my chances of my LLM or my chatbot of actually giving a thoughtful and considerate answer to the user. Mike says, sorry, but I missed the point. Where you introduced the GUI you're using for the parameter setting and tuning? What is it? Which environment? Okay, yeah. So here you have everything on the guide, right, Mike? Here I'm. This is Tara, if you can give the bit.ly link again, just for those people that were late or just had some issues. Yeah. I'm using in here in the guide that Tara is going to link on the chat. Yeah, you will find Uba Buga's web UI, which is the radio interface that we are using, this open source tool, right? You can and you also have here a script that you can run on your server. If you have a GPU instance or a CPU instance and you want to use the interface, here you have like a step-by-step guide on how to install every dependency, all the Python requirements, quantization as well, and you actually get to use this, right? So you see that the generations are actually very good. And that's only with 2 or 3 hours of training, which was like 10 to 15 bucks on OCI, which is, I mean, more than enough, because this could be a chatbot for, like a clinic or something. There are hundreds of ideas. Like you could connect this to a phone answering system, like automated system, like a text-to-speech, then the speech gets asked or asks the LLM for the answer, and then with speech-to-text, you just give the answer back to the user via phone or voice over IP or anything. And just to give you an idea, because I promised that I would show you what quantization is. Quantization is one of the biggest things that are currently being worked on large language model theory, which is to do quantized fine-tuning, right? And we were talking about this matrix, right? Remember that during training, we were saying that the rank of the LoRa matrix is very important. The dimension of the matrix, the bigger it is, the better, because it's going to contain more information, more values. But each one of these values that you see in the matrix, they will be represented either with 32 bits, right? A floating point decimal, floating point operation, 32 bits, or 64 bits if it was a double. But let's assume that at the beginning we have 32 bits. So quantization is going to take the 32-bit representation of any number. Imagine that it's 5.5. Let me put it here, right? Well, minus 5.5. So, and there is float. Float A equals that. Imagine, right? So this is represented in 32 bits, right? Because it's a floating point number. So the thing about quantization is going to take the 32 bits and it's going to either put them into 16 bits or 8 bits or 4 bits, which is just completely extreme. But the idea is that, and just to give you an idea of what's going on under the hood, which is one of my favorite things that I like to do, is that the 32-bit representation, right? If you remember, there's like a standard for these things, which is the IEEE, and then very weird numbers like 732A8B or something, which means that the minus 5.5, if you wanted to represent this, you would get 1 bit to represent the exponent, the sign, so either plus or minus, 8 bits for the exponent, and then 23 bits for the mantissa. So the mantissa is going to consider decimal values, and the exponent is going to consider the numerical part and then the bit. So this might be something like, let's see, this minus 1.5, so it would be like, in a very simplified manner, this would be like 1 because it's a negative value, and then 0, 0, 1, 0, 1, and then for the mantissa, like 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 0. Imagine that it is the bit representation. So what you are trying to do with fine-tuning is to reduce this. So you take some bits out of the mantissa, you take some bits out of the exponent, and then you just leave like 1 bit for the sign, 3 bits for the exponent, and 4 bits for the mantissa. So this would be quantizing this value to 8 bits, right? So you will have to remove some of these values in the middle, right? For the exponent and stuff. And of course, you are losing some values here. You are losing precision. But the good thing is that you are representing every value in your LoRA. Instead of 32 bits, it's now 8 bits. So you are quadrupling down on the size of your matrix just by losing some precision on each one of the values. And of course, this precision actually affects the large language model in ways that is not very common. Like it might take a different route, or it might take a different path, or the rank of the weights of the neural network that are being represented, they will probably have more error. So it will introduce a little bit more error into the large language models, but then you are gaining huge amounts of performance. And this would allow you, for example, to run many of these things that we are talking about. You could run this on 4 bits or 4-bit quantization on a CPU, on a couple, of course you need like a lot of CPUs still, but you could try to do quantized fine-tuning with CPUs, not even needing GPU. And there's a lot of people that are actually researching this very recently, and they will keep doing that for large language models and, image generation. And so this part of AI is really interesting. This is what I wanted to mention. Remember, and also you have this annex here, if you want, with some data sets that are or have already been created by someone, with a lot of examples. Like some of these have like 10 million examples on Chinese. There are also multilingual data sets here. If you want to experiment and play with them, you have them here. And that's all. I hope you enjoyed the session, and we will see you on the next one. If you have any questions or anything, just remember that you can either talk to us on Slack. I try to read every message on Slack, in our Slack channel. And also you can, stay tuned for the things that we do in developer.oracle.com. Thank you, Larry. Thank you for coming. And talk to you on Slack, guys. Tara, you have anything to say?
Yeah, thanks everyone. I did drop a bunch of resources in the chat for you to grab, including the Slack channel, the guide again, upcoming events, where to find them, and then there will be a quick survey that pops up as you exit the Zoom too. So we'd love to hear any feedback that you have on what we covered today or what you'd like to see from us going forward. So thank you again so much, and we hope to see you at the next one.
Yeah, thank you.
Thanks, everyone.